Recall from calculus that integrating is just adding up rectangles, where the base of the rectangle is your differential, and the height of the rectangle is your function value at that point where your differential is located. So, Calc 3, we're going to do the exact same thing. So let's review one-dimensional differentials. The calculus conceit: all curves are really lines, and you approximate changes with differentials. So back to calculus 1. I'm at some point, 3, and I plot the height. And that'll be the height of my rectangle. I calculate my slope. And that gives me a line. The differentials are just changes. So it's my rise and run from my slope. When I'm integrating, I'm going to use dx as my base and the function value as my height. But here, I just want to do the relationships. So, dx is just a change in the x-axis. df is just a change on the f-axis. And then their ratio is my slope. Of course, in Calc 3, we can't divide vectors, so we want to just rewrite. So df, my vertical change, dx, my horizontal change. X is the input to the function, so dx is my input change, so df is my output change. So in calculus, we just thought of them as numbers, positive or negative. Of course, in Calc 3, we're going to make them vectors. So these are going to scale my vectors. In Calc 3, we're going to reduce every problem to a multiple versions of Calc 1. So in the default coordinate system, x, y, and z will take the place of f. So x, y, z are all functions of t, and I can use the differentials to calculate their change as t changes. So let's start with a one-parameter object, a curve. Every point on the curve has some x, y, z coordinate, but we're going to flag it with a t value. Change t by a little bit, and I move down the curve a little bit. Now, holding x and y fixed, only z changes. So as t goes from t to t plus dt, my z only changes by dz, exactly the calculus 1 picture. So dz is just the change in the z coordinate. And by calculus 1, that's z prime dt, our parametric description for z. The tangent vector, since we're in 3 space, we need vectors to describe our motion. dz k, the direction the z-axis goes. What's good for z is good for x and y. So I can vary x, holding y and z fixed. I can vary y, holding x and z fixed. Calc 1 picture again, t goes to dt. A dt change gives me a dx change. A dt change gives me a dy change. Using the calculus 1 picture, dx and dy computed using the parameterization. dx and dy are just numbers. Since we're in 3 space, I turn them into vectors. dx I, dy j. Add those 3 pieces together, and that's my r prime vector. Scaled down by dt. Back to my curve, and if I want to integrate, I want to integrate over lengths. So the standard way we do it is we need the length of the base of the rectangle, and that's our ds. Then we'll multiply by some function value at that point t for a rectangle, sum those rectangles, calc 1 integral. Our ds is just a linear approximation to the curve length, and through our parameterization, that's just the length of our scaled down tangent vector. So now, no matter what base we have for our rectangle, a dx, a dy, a dz, or a ds, we know how to do it.